When we proved the argument principle, we defined the notion of the log derivative of a holomorphic function f as the meromorphic function f prime by f. We even checked that the log derivative satisfies some of the properties which the complex logarithm is expected to satisfy. We did all that without really defining what is meant by the complex logarithm in the complex setting. We are familiar with the same notion in the real setting. However, the notion has to be made precise in the complex setting, which we will be doing in this lecture. Let me begin by recalling what was the logarithm function in the real setting. We will not spend any time on that though. It will be assumed. Let me just recall it for you. Recall that the logarithm ln, I'll denote the real setting logarithm as ln from 0 infinity to r to be the function which inverts the exponential function. Exponential function on r. If we try to define the complex logarithm analogously, we are going to hit a roadblock immediately, because the first observation would be that the exponential function, which is a map from c to c star, which is c minus 0, even though it's an entire function, it's not an injective function. So let me just note that for you. This definition cannot be generalized to define the complex logarithm. Since if you look at the x function e, let me just use exp to denote the function e, which is a map from c to, okay, I'll start using the notation c star here, which is just c minus the origin. The punctured plane is what is denoted by c star. Because what will happen if we try to do it this way, the way we did it in R? If we try to define the complex logarithm just like how we did in the real setting, notice that e to the power z is the same as e to the power w if z is equal to w plus 2 pi I, in fact if and only if 2 pi I k for k in integers. For all the elements of the type w plus 2 pi I k, e to the power w plus 2 pi I k is just going to be equal to e to the power w. So, we do not certainly have injectivity in the complex plane. exp is not injective. So, we can in fact denote, let us denote by log of z, small l, log of z for z in c star. Remember that c star is nothing but c minus 0. So, if you take any non-zero complex number, it certainly has a pre-image under w. We capture all those pre-images. Let the set be, this is a set, log of z is a set w in c such that exp of w is equal to z. So, this is actually a set. We are not defining a function here. In fact, if at all we want to talk about log z right now, that's going to be multi-valued, which is not a function in the sense that we are using the word function. We could specialize a bit more by observing that if w is equal to say ln of mod z, ln here is the real logarithm plus I times theta for theta in the argument of z. So, remember and recall that arg z, arg of z with small a is actually a set. This is basically the set of all theta in R such that z is equal to mod z times e to the power I theta. This is precisely what arc z was. And if you define w to be defined as log mod z plus I theta, then e to the power w is equal to e to the power ln of z, which mod z, which is mod z, and e to the power I theta, which is precisely equal to. So this can be thought of as an alternate description of the set log of z, as log mod z plus I times theta, where theta is ranging over the argument of z. That's an alternate way of looking at it. But this is not something which we will be satisfied with. We would like to really get hold of an honest function f which inverts the exponential function. So let's try to define one such function, and in order to do that, let's revisit from the real analysis setting what we did when we encountered real valued functions. So let's consider a function on R which is not injective, and let's try to see how we defined an inverse of it. So for example, let's consider f of x to be equal to x square, the function from R to R, or to be more precise, from R to 0 infinity. And we can talk about the square root of real number, positive real number, non-negative real number x, and we did work with the square root function quite freely. What did we do there? What did we exactly do to get hold of a square root function? Observe that given any point x in, let me now pick a real number which is positive, then there exists two real numbers, y and minus y, such that y square is equal to x. There exists two real numbers, right? Let me denote it by x and minus of root x, such that root x square is the same as minus of root x square, which is equal to x. And the way we handled this problem was by picking one of these two square roots. So by picking one of these square roots, we worked freely with the square root function. But we didn't arbitrarily pick it. We demanded that the square root function which we picked had some regularity properties. For example, will the function that we get by picking a square root, will it be continuous or not? That is a question which we had to address. So before really talking about that, let me give a small definition. By a branch of the square root, we mean a function g from 0 infinity to r, such that g of x the whole square is equal to x. The question was, what is the regularity assumption that we can impose on g? Can we have g which is continuous, for example? That is the least that we can ask, isn't it? And we did manage to arrange for this by demanding that we pick always the positive square root. So if we define g of x to be equal to square root of x, where the square root of x is greater than 0, we managed to get a branch which is a continuous function. Then g is a continuous branch of the square root. We could define other branches as well. For example, if we pick the function g of x to be minus of square root of x, where square root of x is the positive square root. So in particular, we are picking g to be the negative square root. Even then, g is a continuous branch of the square root. We could pick branches of the square root which were not continuous as well, isn't it? For example, define g of x to be equal, it's defined to be, say, the positive square root for x less 0 less than or equal to x less than or equal to 10, and the negative square root for x greater than 10, let's say. This is also a branch of the square root function, because if you look at g of x the whole square, that's going to be equal to x. However, this is not going to be a continuous branch, because at the point 10 there is going to be a discontinuity. So our goal would be to do something similar with our logarithm. We would like to define by the branch of a logarithm something very similar to what we did for the square root function. So let me give the definition for you. Let omega be an open connected set. In this lecture, if I don't mention omega to be open connected, it's assumed. So all domains omega that we will be considering will be open connected. So let omega be an open connected subset of C minus 0 or C star. Maybe I should start using C star more frequently so that we get used to the terminology. C star is basically C minus 0, and let's pick some omega which is an open connected subset of C star. By a branch of the logarithm on omega, notice that the domain omega does play a big role. On omega, we mean a function f from omega to c such that x of f of z is equal to z for all z in omega. Basically, we are picking one point for each z. We are picking a point from log of z, the set log of z that we had defined earlier. For every z, we are picking some point in the log of z. For example, omega could be just the punctured plane. Let's see what happens when omega is the punctured plane. Let omega be equal to c minus 0. And suppose f is a branch of the logarithm on c minus 0, i.e. f is c from c star to c a function, be a function such that x of f of z be equal to z. In particular, f of z is going to be some element of the type log mod z plus e to the power I theta, where theta is in the set of all arguments of z. One such point is going to be picked, and the question now that we can ask is, what more regularity can we put on the function f? Being a course on complex analysis, our demand would be, can we arrange for this branch to be a holomorphic function? So the question that we will ask is the following. Is it, suppose, can f be a holomorphic function? In other words, we are asking whether we can arrange for a branch of the logarithm to be a holomorphic function on the punctured plane c minus 0. Suppose it can be done if f were to be holomorphic. Let's see what will happen. By chain rule, let's look at the derivative of the function, the composition exponential of f of z, and by chain rule this is just going to be equal to f prime of z times the derivative of exponential, which is the same as the exponential. But what is exp of f of z? Exp of f of z, that is just equal to z, right? Because it's the branch of the logarithm, and hence by the very definition exponential of f of z is equal to z, and this is equal to 1 because the derivative of the identity function is 1, which tells us that f prime of z. So what is exp of f of z? That's just z. because f is a branch of the logarithm precisely, and this tells us that f prime of z is equal to 1 by z. And therefore, if we do have a holomorphic branch of the logarithm on c minus 0, what we managed to establish is that this function f is going to be the antiderivative of the function 1 by z defined on c minus 0. Let's now try to see what happens when we look at the integral of 1 by z over a closed curve around 0, simple closed curve. Let gamma of t, let's pick a very simple curve e to the power it for t in 0 to 2 pi. I just pick the unit circle, right? And since f is the antiderivative which is in C star, notice that this is a simple closed curve in C star, and since f is the antiderivative of 1 by z, we have the integral of f prime of z over gamma to be equal to 0. In C star we have this by the very observation here. We have this is equal to 0 by using the first fundamental theorem of calculus, the complex analog. So I'll just write fundamental theorem of calculus. This is just the complex analog of the first fundamental theorem of calculus. But what do we know about f prime? F prime we know explicitly to be equal to this is equal to 1 by z dz. This is the same as dz by z over gamma, where gamma is the unit circle, and we have checked multiple times that this is actually the value 2 pi I. In fact, it's going to be 2 pi I times the winding number of gamma if gamma were some other curve around 0, winding number of gamma around 0. But anyway, we have picked the curve to be the extremely simple unit circle whose winding number is 1. Even otherwise, we have done a direct computation to check that this is equal to 2 pi I, which in particular is not equal to 0. So we are ending up with some contradiction, right? So hence, if we have a holomorphic branch of the logarithm on C star, then we have a contradiction. As a conclusion, we will not be able to get hold of a branch of a logarithm on C star which is holomorphic as well. We will certainly be able to define some branch by picking one element from the pre-image of every point. However, we cannot arrange for such a branch to be holomorphic. That's what we just noticed. So the next question that we will ask is, what is the next best thing that can be done? Like we were doing many times in this course earlier, we will specialize to a class of domains where we can draw some really nice conclusions, which we did, for example, while we proved Cauchy's theorem. We will specialize to the class of simply connected domains in C, which does not contain the origin. So what is the next best thing that can be done? Let omega be an open connected set of C star, C minus 0. Further, let omega be simply connected. Every closed curve is null homotopic. Now let's see whether we can say anything about the existence of a holomorphic branch. We will come to all that later, but before that, before we even talk about the exponential function or the complex logarithm, the branch of the complex logarithm which is holomorphic, let's focus just on omega and the function 1 by z. Consider f of z to be equal, consider the function 1 by z on omega. Notice that omega is a function which is defined on C minus 0. Sorry, omega is a simply connected domain which is contained in C minus 0, and in particular 1 by z is going to be holomorphic on omega. Consider the function 1 by z which is holomorphic on omega. Also, for any closed curve gamma, by Cauchy's theorem, closed curves in a simply connected domain are going to be null homotopic, and by Cauchy's theorem, since 1 by z is a holomorphic function, the integral of dz by z over gamma is equal to 0. In particular, the function 1 by z is conservative on the domain omega. Its integral over any closed curve is 0. Now, by the second fundamental theorem of calculus, I don't know whether I mentioned whether this was the first or the second. This was by the first fundamental theorem of calculus. This is by the second fundamental theorem of calculus, the complex analog rather, the fundamental theorem of calculus. There x is a function g or maybe f, why to use other notations, f given from omega to c such that f prime of z is equal to 1 by z. This can always be arranged because the function 1 by z is conservative in the simply connected domain omega. So, we do have a antiderivative of 1 by z by the second fundamental theorem of calculus. If you go back to the second fundamental theorem of calculus and go through the lecture once more, you will notice that this antiderivative can be defined up to addition by a constant, and let's normalize our f. Let f be an antiderivative such that given z0 and w0 such that e to the power z0 is equal to w0, we have f of w0 is equal to z0 for some w0 in omega. So, not w0, some w0 in omega, I am right. So, let us normalize it by addition by the relevant constant. We can arrange for our f to satisfy this particular condition. Now, let us see whether we can draw any more conclusions about the function f. What is the function f doing right now? It is the antiderivative, it is an antiderivative of 1 by z, and we have arranged for f to map w0 to z0, where w0 is a pre-image of z0 under the exponential map. Now, if you look at the function x of f of z, remember that f is holomorphic. Since f is holomorphic on omega and x is an entire function, again by chain rule, if you look at d by dz of x of z, this is just going to be equal to f prime of z times x of f of z. Since f is an antiderivative of the function 1 by z, this is just going to be equal to x of f of z by z. So, we know that the derivative of x of f of z is going to be equal to x of f of z by z, and now by the quotient rule, if you look at the derivative of x of f of z by z, this is just going to be equal to x of f of z times the derivative of z, which is 1, minus x of f of z times the derivative of x of f of z, which is going to be equal to x of f of z. So, this is going to be x of f of z the whole by z square, which is equal to 0, because our domain is connected, which implies x of f of z. Hence, this is true for all z in omega, right? And because of that, x of f of z by z is a constant. Let us call it some c. But we had arranged for our f to be special. at for z equal to w0, we have x of f of w0. This is going to be equal to x of z0, which is equal to w0. I hope I have not mixed things up. Maybe x of z0 is equal to w0. Yeah, this is right. So x of z0 is equal to w0, and hence C x of f of w0 by w0, which is equal to C, is going to be equal to 1. And so what we have arranged for is a function f on the domain omega, which satisfies the condition that the exponential of f of z is equal to 1. So look at the route we took here. What we did was that we started off with a simply connected domain in C star, and then we tried to get hold of an antiderivative of the function 1 by z, which was possible by Cauchy's theorem and the fact that omega is simply connected. Because omega is a simply connected domain away from the origin, the function 1 by z was holomorphic on omega, and we could get hold of one such function f. And this function f satisfied the property that the exponential of f of z is indeed equal to 1, and hence f is a branch of the logarithm on omega. So given a simply connected domain omega, we can arrange for a function f whose which is a branch of the logarithm, namely a function f which satisfies the condition that e to the power f of z is equal to 1. Let's now look at a few examples. Let's look at omega to be the set of all complex numbers with the negative real axis removed, minus the set of all x in R such that x is less than or equal to 0. So if I had to draw it on the complex plane, what is happening is the red region is being removed. This line is being removed. Region is not being removed, only a arc which originates at the origin along with the origin, the negative real axis, that is being removed. Now the first observation here is to see that if you pick the point 1 here, any point on C, any point on omega, C minus x such that x is less than or equal to 0, let me call it omega, any point on omega can be connected to the point 1 by a straight line. Let me just highlight that point for you. Any point on omega can be connected to 1 by a straight line in omega. That's the key part. Such a domain is called a star-shaped domain. So in particular, if gamma be a simple closed curve, no need for simple. If gamma be a closed curve in omega, then h of s comma t, which is given by 1 minus s times gamma of t plus s times the point 1. That's going to be a homotopy from at s is equal to 0, this is equal to gamma of t, and at s is equal to 1, this is just going to be equal to 1. So this is going to be a continuous function from 0, 1 cross AB into omega, which is C minus the negative real axis, telling us that omega is indeed simply connected. So let me just say that this is a homotopy of closed curves from omega, in omega, from gamma to, let me just write gamma 1, the constant curve gamma 1. Hence omega is simply connected. and therefore by what we had noted earlier, hence there exists a function, a holomorphic function rather, there exists a holomorphic function f on C minus the negative real axis such that the exponential of f of z is equal to z. There exists a function f which is precisely the logarithm that we are familiar with in the real setting. It behaves exactly in that manner. It's a holomorphic function which is also satisfying the condition that x of f of z is equal to z. Let's see what happens when we have two branches of the logarithm. Suppose f and g be two branches of the logarithm which are continuous functions, The question that can be asked is, can we get hold of some relationship between f and g? One thing that we certainly know is that we know that because both are branches, we have x of f of z is equal to, so where continuous functions, branches of the logarithm on a given domain omega, which is open connected. Then we know that x of f of z is going to be equal to x of g of z for all z in omega, and this tells us that the function f minus g, maybe I shouldn't jump, let me just write it down, f of z minus g of z is going to be equal to 1 for all z in omega, and which tells us that f of z minus g of z is some 2 pi I k for all k. So for k, not all k, for k in integers. In fact, it cannot be all k. That's where the entire discussion is going towards. Notice that f minus g is a continuous function on omega, which is a open connected set. The most important aspect here is that omega is connected, and therefore f minus g of omega is going to be a connected set. Hence f minus g of omega, the image of omega under f minus g is connected. But we know that f minus g of z is going to be equal to 2 pi I k for some k in integers. It cannot be some arbitrary value in the complex plane. Since, okay, this is an exercise for you, you should sit down and check that the only connected subsets of the set, the only connected subsets of the set of all 2 pi I k, where k are ranging over all integers, the only connected subsets are singletons. This is a very basic topology problem which you should sit down and think about. Notice that they are discrete, there are integers involved, and think about what will be the distance of 2 pi I k and 2 pi I L when L and k are not equal to each other. And then that way we will be able to get hold of a separation for any set which contains more than one element. So once you establish this exercise, what do we have? F minus g of omega, which should be a connected subset of this set. In particular, we have f minus g of omega is equal to 2 pi I k0 for some fixed k0 in z, i.e. f of z is equal to g of z plus 2 pi I k0 for some fixed k. k0 in z. So what we have just observed is that if we have two continuous branches of the logarithm on a connected set omega, they better differ by 2 pi I k. And if two such functions differ by 2 pi I k, then e to the power f and e to the power g are going to be equal. So this is an if and only if statement of such that we have defined. So in particular, let's get back to omega, which is c star, which is just c minus 0, and define a special function capital L of log of z, not c star. Let's not go to the setting of c star. Let's go back to the omega which we were considering, the set of all complex numbers with the negative real axis removed, and define this capital L log function. We can define in c star certainly. Let me first define it for you. This is just equal to the real log of the absolute value of z plus I times the standard argument of z. This is called the standard branch of the logarithm. This is defined as, what was capital R? Let me recall that for you. Recall that capital ARG of z was equal to, for z in C star, this was theta, where theta belongs to minus pi to pi, and z is equal to the absolute value of z times e to the power I theta. So this was the standard argument. That is how we had defined the capital ARG of z to be. So we can pick our log capital LOG of capital L log z to be in this particular manner. This is now an honest function because there is a unique such theta in the interval minus pi pi. And notice that if we focus on this domain omega, so that's again another exercise. Sit down and check that this function capital LOG of z is continuous on C minus the negative real numbers. If you look at C minus the negative real numbers, the function that we just defined, the key thing is to notice that the problem comes at pi and minus pi, and that's precisely where the negative real axis, for example, is going to come up. So away from such points, this is going to be a continuous function, and hence, one more thing is that if you look at the exponential of the log of z, what is this going to be equal to? This is going to be equal to mod z times e to the power I times the capital argument of z, which is just equal to z, and hence log z with a capital L is a branch of it's a continuous branch of the logarithm. Is a continuous branch. On omega, which is C minus the negative real axis. But we just checked that any two branches which are continuous should differ by 2 pi I k. Since there already exists a holomorphic branch of the logarithm, which we had denoted by f on omega by the above, I should have called it something, maybe the proposition or the observation. Let me just call it observation. By the above observation, capital LOG of z is just going to be equal to f of z plus 2 pi I k naught for some fixed integer k naught. But then this right hand side is a holomorphic function, and hence capital LOG of z is a holomorphic function. So we in fact have an explicit expression for a holomorphic branch of the logarithm on omega, which is basically C minus the negative real axis. Of course, C minus the negative real axis was just one example of simply connected domain in C star. We could have picked any simply connected domain. We do have the existence. So for example, existence of a branch. So for example, if omega is say the disk of radius 1 around 1, this is a simply connected domain in C star. And contained in C star, C minus 0. And therefore, we can talk about the logarithm, a branch of a logarithm which is continuous on D11. In fact, the log function which we defined here should certainly go through here as well, because when restricted to this function, it's a branch which is holomorphic. However, okay, so maybe I should give one more example. Let omega be equal to d minus 2 comma 1. This is the circle of radius 1 around say minus 2 here. So we are looking at this circle, and here if you carefully look at the capital L log function here, that's not a continuous function. So in particular, you will not be able to realize the capital L log function as a holomorphic branch on this particular domain. So where we are looking for the branch of the complex logarithm matters quite a lot. So observe that there exists a holomorphic branch of the complex logarithm of the logarithm in omega, because omega is a simply connected domain contained in C star. However, also note that capital L log of z, which can be defined on C star by the way, is not continuous here. If you look at the intersection of this disk with the negative real axis, on that line it's not going to be continuous. So in particular, this is not going to be a holomorphic branch, the capital L log function. We do have some other branch which we can get for the holomorphic branch for the complex logarithm, but this is not going to be one. So it depends. The point that is being stressed and pushed forward is that when we talk about the holomorphic branch of the complex logarithm, it matters which domain we are considering. Let me conclude this lecture by using the knowledge of branch of the logarithm to construct branches of some other functions which are not injective. If you go back to one of the problem sessions earlier, recall that given W in C star, there exists n roots to the equation z to the power n is equal to W. This is one of the problems which we solved in one of the problem sessions earlier. Now the question can be asked, can we talk about the nth root function in the complex plane? The same problem comes up, the problem of choice, in the sense that given a point there are n pre-images, so we will not be able to get an honest function in a very simple manner. We will have to pick again by a branch. So I will not define what branch of the nth square root again is, it's just the same definition. Goal is that we would like to obtain a holomorphic branch of the nth root function. Just so that I am not being ambiguous with words here, i.e., does there exist f from omega? I will not use f, f was already taken generally to denote the complex branch of the complex logarithm, branches of the complex logarithm. So let me pick g from omega to c such that g of z to the power n is equal to z for all z in omega. Does there exist a holomorphic function? g from omega to c such that g of z to the power n is equal to z for all z in omega, where omega is simply connected. Well, where omega is a subset of C star. Well, we are going to work on simply connected domains because that is where we have proved the existence of a holomorphic branch of the complex logarithm. So let's specialize to a simply connected domain. Again, as mentioned earlier, omega is an open connected set. Let omega be simply connected now. Open connected subset of C star. So in particular, 0 is not in omega, and further omega be simply connected. Let f be a holomorphic branch of the logarithm on omega. So notice that because it's having a holomorphic branch here, any continuous branch is in particular going to be holomorphic, which we had noticed earlier. Now, using this holomorphic branch, let's try to get hold of a holomorphic branch of the nth root function on omega. Let's define g of z to be equal to the exponential of f of z by n. Notice that exponential of f of z is equal to z, but we are now looking at exponential of f of z by n. Being a composition of holomorphic functions, notice that f of z by n is a holomorphic function, exponential is an entire function. So exponential of f of z by n is going to be a holomorphic function. We have g is holomorphic on omega. Further, g of z to the power n, if you notice, this is going to be equal to the exponential of f of z by n, which is just e to the power f of z by n, the whole to the power n, which is equal to the exponential of f of z, which is equal to z, and this is precisely what we were trying to get hold of. So hence, on simply connected domains, we have a holomorphic branch of the nth root function as well.